Hello, this is the next video in a playlist that I'm calling combinatorial results. And here we're going to look at the probability of ever touching a diagonal point in a random walk. We're going to answer two questions though. And each question, is going to use the Pascal triangle or the Catalan numbers. So let's get started. So first, consider a grid. The starting point is at the origin 0, 0. You go up with probability P and right with probability 1 minus P. So the first question we want to look at is what's the probability of stopping at the n point after 2 n steps? Then the second question is what's the probability of ever touching a point n, n as n goes to infinity? Now the first one, there's lots and lots of videos on this, so I won't go in too big of in depth too much. So 0, 0. So each move we can go up or down with probability P or 1 minus P, and we want to get to there. But in all cases, we have to go right 4 times and we have to go up 4 times. So, but we also have to think about the number of paths that we can take. Each path is independent. And each path has the same probability of p to the 4th, 1 minus p to the 4th. So we just have to calculate the number of paths. And the way we do that is with the Pascal triangle, which again, I'm not going to cover in great depth because I think everyone has seen it. And these numbers here are the binomial coefficients. So if we take this and go sideways with it and think about it like this. So it starts at 1. And then there's one way to go here and one way to go here. And then here, there's one way to here, there's one way to get to there. There's 2 ways to get to that point, this way or that way, and that corresponds with this 2. And there's one way to get to this point. And then each way, this grows using Pascal's triangle. So the point 4, 4 has 8 to the 4th pass ending at 4, 4. So the probability of stopping at that point, given you've gone 8 tries, is this binomial probability. And that's it. Now, one thing I note is this probability goes to 0 as n goes to infinity. The further you go out the path, let's say you go 100 steps, what's the probability you're at the 50, 50 point? That's starting to get pretty small. And if you keep going out and out and out, that probability goes to 0. And so then that kind of triggered me, well, what's the probability of ever touching a diagonal point for any P? And that's what the second question is trying to address. And we look at the Catalan numbers, and it's represented by Cn, and it's just a sequence of numbers, 1, 1, 2, 5, 14, 42, 132, and it has several different applications, which is kind of amazing. So this is the C0, C1, C2, C3, C4, C5, using the Catalan notation. Now, one of the interesting things is that the Catalan number represents the number of paths in an n by n grid not crossing the diagonal, but reaching the point n, n. So as a quick example, and here's the formula for the nth Catalan number. If C equals 0, then there's only one way to be on that point, and that's what that represents. Now remember, we start in the lower left, and this is the 1, 1 point, and there's only one way to get there. Now notice that I'm not adding the numbers above it because you can't go past, you can't cross the diagonal. Now here, we start here, and there's 2 ways to reach this number. 1, 2, right? And again, I left these dots off because in this algorithm, you can't cross that path. Here there's 5. 1, 2, 3, 4, 5. And that's what these Catalan numbers represents. And we're going to make use of these in this proof. to illustrate what's going on. So let's let xn be a random variable, and it represents the number of moves right in n moves. So n can be 0 to n, right? Those are the values it can take on. But we're going to let the variable dn be, the event that all the paths do not touch the diagonal within n minus 1 moves. And the reason that we want that is, if we're going to look at the probability of achieving this point, remember we're looking for the probability that you touch the diagonal. So if we're looking at the probability being on this diagonal and we touch a previous diagonal point, then this one's irrelevant. We've already touched the diagonal. So we need to assume that none of the paths have touched this diagonal already. And so that means then this probability that the path touches the diagonal is actually the sum of these probabilities. So this is the probability that we're on. So we start at 0, 0. So this probability is the probability we're right there, right? And not touching a diagonal before that. But there's no there's no way to cross the diagonal. So this is sort of irrelevant. So here, this says the probability that x4 is equal to 2. So in 4 moves, 1, 2, 3, 4, we're at this point, but we haven't touched that diagonal element. So that's what this D4 represents. In 4 moves, we haven't touched that diagonal until we get to that one. So, and then what's that probability? And here, this is the probability that 1, 2, 3, we're at this point, but we haven't touched the diagonal prior to that. So it's we're trying to find mutually exclusive events. So there's 1, 2, there's a number of different ways to reach it. And then we let n go to infinity. And so this is the probability. This is it. But that doesn't tell us anything about what what values it can take on. So, but this was the big discovery in my mind of me calculating this. And maybe other people have done this before. I don't know. This was just me trying to have fun and working it out. So this first probability, the probability that we're right here, is you have to go over 1 and up 1. So that's what this probability represents. C0 is 1, so it really doesn't change it. But there's 2 ways to get there, and both of them have the same probability. So this is the probability of being on that point. Now this one, the probability that we're at that point right there is, you have to go over twice and up twice, no matter how you get there, right? But and we can go the bottom path or the top path, and so that's what the 2, because all the paths are equally likely. So let's just study the lower paths, and let's use the Catalan numbers, right? To get here without touching the midpoint, we have to start there. But now look at this lower triangle here. What are all the number of paths that we can go through here and end up here? Because the next one, it's deterministic. You have to go to that one. Well, the number of paths in this little triangle is the Catalan number. Now, to get to this next point right here, right, the 2 is because both paths are up above the diagonal and below the diagonal, equal to likely. And we have to go over 3 and up 3 every path. So now let's calculate the number of paths. So the Catalan number for 2, remember we're trying to get here. We have to go here, so that's step 1. But now look at this triangle. It's all the number of paths in this little triangle to get to here. But then, of course, the next one's predetermined. It has to be you go up with probability P. But the number of ways to traverse that triangle is Catalan 2 number. And then this number is this. It's the same way. You have to go over 4 and up 4. And 2, because the number of paths here is the same as the number of paths here. So let's look at this number. So what we do is we pick this triangle, and it's the number of paths that you can go through here to get to there, and the next one you're forced to go up. Well, that's this number. And you just keep doing that for infinity. And so each of these is it. And so the probability is this. It's the exact probability. But now you got to think, well, is this a convergent sequence? Or not sequence, series. So if we do the ratio test, we take the n plus 1th term divided by the nth term, and that's these two. And we get lots of cancelizations here, which is this. This divisor goes here, and all the factorials can be reduced to this. Now this limit is, there's no n here, so it can come out front. This limits to 1. This limits to 2. This limits to 2. So this is the answer. Remember, we're doing the ratio test. So this is less than or equal to 1 for all p except for p equals half. So it's always below 1 for all p except for 1/2. And it equals 1 when it's a half. So that says for these p's, it's a convergent sequence. And this one we don't know, but it turns out that it is convergent for this point here. So thus this series, which is the probability of ever touching a diagonal in the grid, is a convergent series. Now from Wikipedia, the generating function for the Catalan number is this. So it's a polynomial with the Catalan numbers as the coefficients. And it has a closed form expression as this. And you can find that on Wikipedia. But I also recommend a video by Michael Penn for deriving this. It's quite fascinating, by the way. But we're going to make use of this. So the probability that the path touches the diagonal, we said was this probability, but now we kind of have to trick it to look like this. So if we take out the 2 and we take out 1p and one of these 1 minus p's out front, and then we can rewrite it like this. And so this looks just like that generating function with p 1 minus p plugged in. And that's what it is. So now we plug in p 1 minus p to this closed form expression, and we get here. Then the 2p 1 minus p cancels here, and we're left with this. But this polynomial here can be written as a square. Now the square root of a square comes out, and don't forget the plus or minus this. Now, in order, you remember we're looking at probability, so probability has to be between 1 and 0. So the only ways this to work is if p is between 0 and 1/2, then this is the answer. And if p is between 1/2 and 1, then this is the answer. And that's the probabilities of ever touching the grid. And what I find quite interesting is when p is 1/2, the probability is 1 that you will touch that grid at some point. And everybody knows a random walk with a 50-50 left or right has such a large variance, huge variance. So that's not surprising. But to me, any other number, the probability is not 1 that you touch the grid. And I found that kind of surprising. Well, I hope you enjoyed this video. I sure did. Please like it, subscribe, so you don't miss the next one. Thanks, bye.